Hello, this is your old machine shop instructor, Ed, the CNC dude here in Sarasota, Florida, and on one of our rare non-sunny days today, but Friday. I'm going to continue on part two of tricordial milling strategies from a layman's version. My cat wants outside the room. Okay, hang on there, Tinkerbell. So, all right, this is a great guide I downloaded, and I've done some other readings, but this is from the Harvey Tool Company, Helical. They sell helical end mills too. Got some nice pictures here. Reading up about high efficiency machining. So you hear HEM or get off my light here. High speed machining, high efficiency machining. It's a new trend. It's CAD CAM manufacturers have come out with a tricordial, they call it, style of machining versus the classic version. Let me get through some of these here. Yeah, they talk about what CAM software does your shop use for HEM, and they got CamWorks, Gibbs Cam, Fusion Master Cam. Gibbs Cam is very popular in California, I think. Why doesn't your shop use HEM? I think I'm finding out through my research the last year into my dive into this is many companies are unaware or unsure how to use this. I know I worked at a shop and we had Mastercam, and we knew nothing about how to use the dynamic milling thing. So a lot of times you're not going to experiment with something you don't really know, um, unless you see a demonstration or something like that. So right here, I haven't learned enough yet. Our current method works fine. Our current machine can't support it. A lot of these are not as true as you think. Here's a nice, looks like a Cat 40 holder with an ER collet and a multi-flute end mill here. Nice picture. And here, traditional machining. I started CNC machining in the 80s, wrote hand code. So we didn't have all the uh, positives that CAD CAM brought to that. But either way, we were machining like this. And I like they have the red color here, like it's bad. But that's how we would do. We would do like half the cutter was like a standard step over, and you would realize you couldn't. We used to like drill a hole in the material and then put the end mill in a set going around. And then we learned how to ramp mill, which was like sideways, zigzagging in, like either as a spiral or just a straight line. But the step down technique was pretty common. And then you had the corners. The corners were an issue. So if you had a pocket that was 0.25 radius, and you're using your go-to half-inch end mill, when you get into the corner, it's like got 90 degrees of contact, and you'd always end up with like chatter marks and stuff. So, and a lot of it, I was working in like military defense stuff, and that was unacceptable in the corners. So we'd have to come up with other strategies, especially if the pocket was very deep. So it was a lot of like heartache how to get all this stuff to work. It wasn't more about horsepower, and machines had limited RPM, and even when you get into higher RPM, you could get more MMR, they call it now, material removal rate, but you still have those limitations. High efficiency milling is wanting you to actually use the whole tool, which this was always like unused up here. We always have these end mills that were worn out down here, and they were pristine up here. So you're using the whole length, and instead of like going down in steps, we're going sideways in steps. But you could never write that by hand, and it has to generate a ton of code. And also you could do it like multi-passing, like smaller increments at full depth with traditional CAD CAM or hand code styles. But to get into the corners was always is the other issue. So there's like two ways of why does trochoidal style milling improve. Uh, it's got to do with full depth cutting and also corners. All right, here's a typical case study here, traditional high speed. I still call it high speed. Here's an end mill they make. This is a coated end mill, carbide, and this is rougher. Typically, I always want to have rougher and finish tool. I come from production machining, so if you do I like Titan's method of using the one tool for roughing and finish, and it can do it just fine. And but in the industry, finishing tool may start looking not so good on the finish. Not bad, but not pristine. So you try to keep the finishing tool, especially if you're trying to size something, in good condition with light cuts, and you let the roughing tool do all the work. Okay, some nice pictures in here, and there was a discussion here like HSM versus HEM, and I like pictures, and I'm not an engineer, so I think we learn engineering by doing. All right, if you look at your feed and speed charts, I'm going to go into this chart right here. This is a typical chart, and I still hand this out in class because we need to at least get to this level. Right up here, if you're cutting aluminum, and they say recommended surface feet per minute is 600 to 1200, and this is called chip load up here, and chip load is based on this 50% step over, half the end mill, and so this size right here would be the size of the chip when this thing goes over. So in the calculation, if you do the calculation, is if you got 4 flutes and 1 rotation, and this was like 2/1000 times 4, which means it would travel 8/1000 of an inch in this direction. Of course, the machines are running in inches per minute, so you got to add that in because you got to add the revolutions per minute in there in order to get the inches per minute calculation. With the modern high efficiency machining, you're taking less what they call radial step over here, And in Fusion, I believe it's optimal load, and Mastercam, it's I think it is just called step over, percentage of step over. So your chip is actually getting thinner. They call this chip thinning. So you're using your standard numbers, and then it's really only taking out this small amount. It's sort of, in other words, the tool is able to, it's actually cutting lighter. If you actually, you could see it on your load meter when you're running the machine. So we learn by doing and say, oh, let's turn that up another 50%, and the load meter's chugging along fine. And so that's how we learned, like, geez, we were running at 40 inches a minute. It looks like we can go like 84 inches a minute. But there are some calculators out there, and they actually had a long, I got all this math. I don't like to do too much math, but you can actually make your own calculator, or you can go online. This is the ISCAR Tool Advisor. I just put in some standard stuff here. They got metric and inch, and that's what they're talking about. They're talking about this MCT number here. So I would plug in like a half-inch end mill, 0.1. I don't need any of these numbers, engagement ratio or engagement angle. They actually can figure out the angle here. So it says angle, TEA is angle. This is 90%. This is 41%. But I'm just plugging in some numbers. I said 3 flute end mill. I want to get my surface feet that would be running in my machine. So I got an 8,000 RPM machine. If I put in 1,000 and hit calculate, I'm at 7639. I'm still good. And I'm going to put in, let's go back to this book here, 2 to 4 thousandths. Let's go right in the middle, right in the middle, 0.003. And I'm going to go full depth because I'm going to use the adaptive, right? Calculate. Okay, at 3 thousandths, you're actually at 2 thousandths of 4 tenths. And this is your feed rate, inches per minute. So you got 3 thou at 7,600, and you're running 69. I know a lot of people that would be afraid to even run that. And then they had some, I gotta look, recommended with chip thinning. Okay. So in this case, I'm only getting 2.4, so I need to bump this one up. And maybe I'll use these as my parameters. Now I'm in the 3.32 range, 3 thou plus, and I'm at 92 inches a minute. So when I get into my fusion, I'm going to plug in surface feet per minute and chip load, this number right here. Let me pull that up in the background while I continue to talk about that. Go back to here. So I wonder why the CAD/CAM people don't have this built in. I think Mastercam has it, but you have to have a certain tooling package in there. It would be probably really good if we can get to the point of you pick the tool and you say it's cutting a material and you get it all to combine together. It's usually done on the side. You got to do those calculations on the side and then plug them in, and then you can kind of build your tool library around that. So, but to just get knowledgeable about this. All right, here we go. Fusion coming up. I'm going to plug in my Titan mill. 7M I was working on, and I was doing soft jaws. Titan 7M right here. Coming on up. Okay, I actually added in these manual NC comments. You can put them in right here, manual NC. Just thought I'd show you that while I'm here. Edit. So I have it, I put a comment in the front, and it was like on stock size, you know. So if I spit out the program, I have stock size, I have a comment on setup, and a comment on, this is a funny one right here. We just did this as a laugh. Wake up George. So that's in the program. Okay. Let's go to the adaptive. Here's our adaptive strategy, right? And what do we have in here? We got, I'm using my tool library. I made a secondary library up here. I had my original Titan one, and then I went in and adjusted some numbers. So my 1/2 inch flat end mill is going to come out of the gate at 6,000 RPM and 2.5 thou per tooth. And it's a 3 flute end mill. You got to build that into your data. Right here it says 3 flutes. Okay. So it'll do the calculation for you. So this is based on our lowest horsepower, lower RPM machine, the TM1, and the max RPM is 6,000. So over here I get 6,000 RPM, because if I started to use the SFM numbers that were in the chart, like if I start at 600, I'm at 45. I'm like, no, I can go more. I can go up to 1,200. That's 9,000. That's too much. Let me. Or you can plug in a hard number. You know, like you get in this weird number here. Let's try 900. 68. Okay, so let me say forget it. I'm just going to put 6,000 in. 6,000. All right. This is my feet per tooth calculation, which affects that number right there. So that's 2.5 thou per tooth. But let's see, linking parameters. Where's Where's my optimal load? This is, you're right here. It gives you a little picture. It says maximum amount of engagement, which is sideways. No HSM, HSM. Traditional pocket, they give you a little story to get overload the tool, results in faster removal. Okay, so this is 75 thou chip load, right? You know, we're using, so let's go into the calculator here. Let's pull up that calculator. So we'll make this like 0.075, and I had 0.0025, and I'm going to recalculate. Oh no, let me make the RPM correct, which was, this one you cannot overwrite the RPM. It's the only thing I don't like about it. Calculate. I'm getting in the ballpark there. Let's try 775. Close enough. Okay. 3 flutes, 2.5 chip load is actually at 1 8/10. So, oh, almost right. 3. Was I at 3? Let me check. No, I'm at 2.5. Okay. But I'm going to say, I'll base it on, I got to have some kind of starting point. So, those are good. A 3 thou will give me really a 2. So let's raise our standard here. And we're almost a 3. 0.0042. Let's play with the numbers. And now it's 3. And that is 75 inches a minute. So I go back to here. So I got to actually plug in that number. No, actually, I'm wrong. I got to plug in this number right here in order to get this kind of chip load at this step over. That's the 3 things. And I forgot what number it was already. This is why I think maybe they can come up with a way to do this internally. So we want 4 thou and 2/10 to end up at 3. Okay. This is why a lot of us just do it at the machine and find out, and then we come up with our recipe. I hear John Saunders saying that a lot. Go back to here. So we want 4 2/10. So you go 0.0042, and now we're at 75 inches a minute. So notice these say 45. These are hard numbers you get. They're not based on any calculation. Lead in, lead out, and ramp, and then plunge. And plunge is based on this feed per revolution. Personally, I for a ballpark, I like to make my ramping, but ramping and plunging is not chip thinning formula. It's kind of plowing its way in. So I probably have to think about my original number, like 50, or so you got to come up with some parameters. Maybe make that 25. So feed per revolution. This is actually going to calculate based on the tool, and that's how much it takes out per revolution. So if I made that 0.0075, it becomes 45. Hey, for some reason it jumped these up too. Okay, maybe it is connected to those. Okay. And when you do this, this is going to recalculate. Jump this out of here. And if you do your analysis here under simulate, you can check your machine time. And you can actually, in your settings, turn on preferences. Let's see. Manufacturer, show cycle time. So that should be coming up here. Or show operation machining time. Hit apply. Okay. Maybe these are spread out. Oh, they're right there. So right there, 2 minutes, 55 seconds, 35 seconds. So you can kind of tell right off the bat where your problem areas are at. Obviously, this is the one with the most material removal, and the other ones are just standard cutting. Okay. So that's a pretty baseline talk about this, and very small end mills. Then you got your radial depth of cut and axial depth of cut, how much you're going to take out. So in this calculator here, I plugged in, where is it? Axial depth of cut 750. It's not asking me about horsepower, but they're saying here recommended 5 and 9/10. So this I would need to know a little bit more about, but I would not, just from experimenting, and you can come up with your own recipes. I guess I like that term recipe. It's more applicable, but you're kind of stepping up from the calculations that are based on this, using these charts. We at least got to get to this point, and then we want to jump our game up. We're starting to learn how to use chip thinning and step over. Now, if you're using Pocket is not the same. Pocket's going to be based on Classic. So if you're using Pocket, let me just pull this one up. Let me get this out. Yeah, hit Pocket. Let's say I'm adding an operation. I'm doing Pocket. And that one is finishing. This is plain step over right there. It's not doing any right here. See how it's looping right here? Because normally you would have just gone in and went, and you get to the corner and buzz, or you just kind of plow yourself around. This one's kind of looping its way, loop, 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 and as it'll cut in the climb milling direction and reposition, climb, reposition. So getting back to one more setting here that I talked about was this one right here, lift height and non-engagement feed rate. Lift height means as it retracts and repositions, how high up do you want it to go? And I put 10 thousandths. You just need it up a little bit. This one's going to be what feed rate do you want to do when you reposition. It's still going to be a G1 move, but if you're running at 75 inches a minute, if you didn't set that, you'd be going back at 75 inches a minute, which would still work, but this is taking advantage of more high efficiency. You're going to, our BF2, it comes out of the gate at 650, and I think we have it up to 1,000 right now, is we reset the parameter on that. So it repositions at 1,000. And this could, shave time off here, and safely, very safe, yeah. All right, so just my quick talk on this. This can be a very deep subject, but I think if we take it off in little chunks, you can learn more about it. Okay, I like this when I found this calculator here. So, and actually, once if you're doing certain work all the time, you don't really have to go into the calculator all the time. You get some basic parameters, and then you might even set up like templates of similar jobs. I did that with CO2 dragsters we were making, and I would bring in the new model, and all the parameters are already there already. But that's personally, if you're teaching people, you want them to do all the steps, so they can get in the habit of knowing what all these settings mean. Okay, so that's my 2 cents on even my own personal learning and what we were trying to teach. Okay, thanks, and have a nice weekend. I'm going maybe drag racing tomorrow. A bunch of us have rented the track, as long as we stay away from each other. Okay, talk to you later.